Okay, and now we come to the last portion of this this submodule. We're going to ask some questions that we completely ignored when we were plowing through how to get the solution of a first order ODE. For example, you want to know, can we always find a solution? If not, what conditions do we need on those functions P and Q so that we can get a solution? Does a solution exist on all of R, or does it exist on some restricted interval? Can we tell from knowing something about P and Q? So those are the kind of questions we just skipped over and went right to solving. And now we're going to look at those questions a little bit more carefully. So if you remember from last time, we looked at our first order ODE. And let's just go directly to say we have it in this form. So y prime plus p of xy equals q of x. And we showed that the solution is y of x is equal to 1 over mu of x times the integral from, let's say, well, okay, x0 to x of mu of x q of x dx, where mu of x is e to the integral p of x dx. Okay. And in here, this is a definite integral. So this goes from, so you get the value at y of x minus this thing evaluated at x minus the value at some point x0. So we're going to think of having an initial condition at, say, y at x0 is equal to y0. Okay. Okay. So the question is it always true that we can do this? And when, and the answer is obviously no, not for every p and q, because you can get things at q that functions that are not integral. So functions p that are not integrable. So this thing wouldn't even make sense. So it can't be a perfect, they can't be perfectly arbitrary functions p and q. So what is true? So the theorem, and I should say that we will state some theorems in this class, but we will be almost never be proving theorems, because the proofs of the theorems of these ODE, standard ODE theorems are generally a little bit tricky, and so they're sort of beyond the scope of an introductory class. But the statements of the theorems are important because they tell us when we can apply the methods we just learned. So suppose P of x and Q of x are continuous on an interval, let's call it I, from, say, alpha to beta, on some open interval I, period. Then there is a solution there exists a unique solution phi of x to the problem y prime plus p of x, y is equal to q of x, y at x0 equals y0, where y0 is an arbitrary but prescribed value. Okay. So in other words, as long as those coefficient functions in the inhomogeneous term are continuous on an interval, you're guaranteed to have a solution on that interval. And this formula, if there is a solution, this formula will give it to you. Okay. And then you have to pick, there comes an arbitrary constant out of this integral, and then you have to pick it correctly to make it satisfy the initial condition. And without the initial condition, you still get a solution, it's just no longer unique. Okay. All right, so let's look at how that, and so let me say one other thing before I go on to this. So the solution will exist on the entire, is on the interval that is chosen as large as possible so that P and Q are both continuous. Okay. So you have to have both of them be continuous to guarantee that you have the solution. Okay, so let's go back to a couple of our examples that we did before. So if you look at the example we did, the first one, we looked at xy prime plus 2y is equal to 4x squared, and we had y of 1 equals 2. And we worked it out, and we got our solution was y of x is x squared plus 1 over x squared. Okay. So notice this thing is, notice y is undefined at x equals 0. So this solution can't exist for all real numbers because it's undefined at 0. So how could we have seen that we were going to have a problem? Well, you don't look at the equation in this form. You write it so that you have that coefficient being 1. So this is 2 over x, y is equal to 4x. Okay. So again, that's what we did when we went to solve it. And remember, this is our function p of x. And here is our function q of x. And so are p and q both continuous on all of r? Well, q is just fine everywhere. It's a polynomial, so that's good. That's continuous everywhere on r. But p's some trouble for us. P of x, p is discontinuous at x equals 0. So this equation has a unique solution on either the interval from minus infinity to 0 or the interval from 0 to infinity. And which interval your exact solution lives on depends upon where your initial condition lives. So this initial condition lives where x has to be able to take on a positive value. You have to be able to make sense out of x equal 1. So for the condition y of 1 equals 2, we need the solution to be defined at x equals 0. So we need the interval from 0 to infinity. Sorry. If I had given an initial condition, say y at minus 1 is 2, then we would have wanted the other interval. Okay. So let's look at the second example that we did. That second example, now let me find that. Our second example was xy prime, so this was example 2 from the last video. Xy prime plus y is equal to x ln x, and y at 1 is equal to 0. Okay, so notice if we rewrite this, we have y prime plus 1 over xy is equal to ln x. Okay, and so again, we have a problem. The solution will not exist everywhere because p of x and q of x, so p and q are both discontinuous at x equals 0. Okay. So we don't expect our solution to be nice at x equals 0. So that means, and now a little bit different from before. So it says we can't hope for x equals 0, but we could hope from minus infinity to 0 or 0 to infinity. Could we do that in this case? Well, the answer is no, because q doesn't even exist if its argument is negative or 0. So the only hope, so we need the interval 0 to infinity, because p will be continuous there, and q only is continuous and only lives here. So we don't have something like, it's a different situation than we had in the previous example. And in fact, when you look, we had our solutions worked out to be exactly why the general solution, well, okay, I do have the initial condition there. So the explicit solution for the condition, for the equation with the initial condition that we were given was exactly this, okay? And notice that solution is undefined. For x in the interval, it's undefined for x in the interval from minus infinity up to and including 0. So this solution only makes sense. I'll say only lives. It means only makes sense on the interval from 0 to infinity, because the log is undefined anywhere else, and this thing is not good at 0, and the log would be undefined there anyway. Okay. So basically, by looking at the coefficient functions, we can tell when we have a chance of having a unique solution and when we don't. Okay, that's it for this little piece.